Okay, so we have another equation, another equation. We have another problem, which I drew some equipotent lines around a negative charge, which is this guy right here. So that is the negative charge right here. And then we have some equipotent lines surrounding the negative charged object where the potential difference between any two adjacent lines is the same. So the potential difference is the same. And it wants to know which region the electric field is greatest and what direction the electric field is the electric field in that region. And then which equipotential line has the greatest potential. And so right off the bat, I thought, we're talking about electric field, so let's look at the equation E equals KQ R squared, where R squared is the distance from the charge to the field point. And so because of that logic of just the equation, knowing that the electric field is inversely proportional to the square of the distance, we know that it's most likely going to be highest on the right side of the particle. But also, there's another indicator from this as well, because the lines are more dense right here. We can also determine that the electric field is going to have a greater magnitude on this side comparatively to this side, which has way less dense lines. So that's just another way of putting it. So we would say that we would say that the electric field has greatest magnitude on the right of negative charged, I don't know how to spell, charged particle. So then let's draw that in to our picture here. And so this side is going to have E, electric field, being the greatest. I didn't draw an arrow yet because we're not to that question. So now it wants to know the direction in that region. And so I left it without an arrow yet. But because this is negative, that means that the direction of the electric field is going to be leftward of the object. So like that's a terrible way to say it. It's going to be going inward. We know with negative charged objects, the electric field lines go in. And so we know that, hopefully you can see that, the electric field is going to be pointing inward, so to the leftward. That's a weird way to say it, but okay. So then it also asks which equipotential line has the greatest potential. And so what we can do here is think, okay, let's see if I can, so here's number 1, let's say, number 2, and number 3. So, yeah, 1, 2, and 3, if that makes sense, and hopefully it focused for you. So 1 being the most inward, and then 2 being the second layer, and then 3 being the outer layer. And so it's asking us which equipotential line has the greatest potential. And so the outer equipotential line is going to have the greatest potential, I'm pretty sure. I mean, that makes sense. Let me think. Yeah, okay, so with okay, so going off of, okay, so we have a negative charge. That's known. And with a negative charge, the potential decreases as you get closer in distance. So, meaning inward, as we go in, so say to layer 2 or to layer 1, the negative charge potential is going to decrease. Or the charge potential, not the negative. The charge potential is going to decrease. And so that would put us with, so 3 being the greatest potential. So essentially, the outer layer is going to have the highest potential. Okay, and so there we go.